Our obstacles are made up of three separate classes. We've placed them all inside of a package called obstacles. They are anemone, which essentially pastes together top tentacle and the rectangular tiler. It then flips the object if it's upside down. Obstacle, which takes the top obstacle and pairs it with the bottom obstacle with a randomly spaced gap in between. This class also contains a collision detector for the paired objects. And finally, the Obstacle Manager class, which manages the obstacle's movements on the screen as well as the amount of obstacles on screen at any given time. Let's start with the Anemone class. Our Anemone class extends a bitmap, gets past four variables, a height, a top, which is a tentacle bitmap, a mediator, which is a rectangular bitmap, and upside down, a boolean that tells us the orientation of our obstacle. It looks something like this. Inside our constructor function, we then calculate how many tiles we need of our mediator bitmap. To find this, we take our desired height, h, and subtract the height of our tentacle bitmap. So const tiler GUI vertical tiler, which is another Gingy tool that automatically tiles the same object to a specified height. And we then create a container, a new top piece, and a new mediator bitmap. We set the tile's location to the bottom of the top piece, and we add both the tile and the top. So tl.y equals top.height minus 1, which sets the tile position to the bottom of the top piece. Remember, this is for obstacles pointing upwards. And container.addChildTL and container.addChildT. Now let's quickly create a variable that will contain our bitmap data. We'll call this BMD. And let's add an if-else operation to delineate the operation depending on whether we need to flip our obstacle upside down. You'll notice that we go through a few steps if our bitmap data needs to be upside down. This is because we need to patch the fact that AIR's bitmap data ignores the scale y parameter. If upside down, const anemone bitmap equals bitmap_tools.create bitmap container. Essentially, we're creating a bitmap out of the container. Now anemone scale y equals -1. And const new container sprite equals new sprite. New container.addChild anemone. And we'll get the bitmap data. This patches the fact that AIR's bitmap data ignores the scale y parameter. So BMD equals bitmap_tools.create bitmap. New container.bitmap data. Else we'll have our BMD equal to bitmap_tools.create bitmap data container. And let's pass our BMD through our super function. Easy enough. Let's move on to our obstacle class. Our obstacle class extends sprite and has three variables that we have to reserve memory for. These variables are the non-visual object, top gap, which is the top's calculated position, bottom gap, which is the bottom's calculated position, and a passed boolean that tells us if the turtle has passed the obstacle. Before moving on, to make our lives easier, let's create some internal static variables that will act as references of our turtle and obstacle objects. We'll separate the section with a commented heading. So let's have a private static var top, which is a static reference to the top assets. We'll have a static reference to the filler, the turtle stage x number, the turtle stage back number, the turtle height, which is a number, and the turtle ref, which is a turtle altogether. Filler is just a mediated display object. Underneath these references, let's create a new public static function that is passed to turtle and updates all of our static reference variables. So public static function init, we pass through the turtle, and turtle height equals turtle.height. Turtle stage back equals turtle.getBounds GUI module settings dot stage underscore ref dot x. Turtle stage x equals turtle stage back plus turtle.width, and turtle ref equals turtle. We can also perform a check here and create our necessary assets if we haven't already done so. So if top is null, top equals assets manager.getImage top, and it's in our animations atlas spreadsheet. And we'll do the same with our filler display object. Great. Let's turn back to our obstacle class and call a function called recreate from our constructor class. This function will create anemones. So public function recreate, past equals false, remove children, which will remove previously added anemones if they exist. Let's continue by adding some constants into our recreate function. After, I will explain what each one does. Half gap, which is a number, min, which is the top height plus the filler dot height plus half gap, max, which is a GUI module setting stage ref dot stage height minus min minus half gap, and middle, which is a number, and it's the number tool dot random range min and max. Half gap is half of the gap between the top and bottom anemone. Min is the height of the top anemone. Max is the height of the bottom anemone. And middle gets a random number between min and max. Let's save the top and bottom as positions. Underscore top gap equals middle minus half gap. Save top's position. Bottom gap equals GUI module settings dot stage ref dot stage height minus underscore top gap plus game settings dot obstacle gap, and this saves the bottom's position. And let's add our variable obstacle gap to our game settings class under a heading called obstacle settings. Public static var obstacle gap, and we're going to set it equal to 200. Next, let's create constant variables that will hold our top and bottom anemones and add them to our stage. Const t anemone equals new anemone, and top gap top filler and true. And we'll do the same for the bottom anemone, but instead we'll do bottom gap top filler and false. We'll add these obstacles to the stage. add child bracket t, and add child bracket b. And finally, let's set our bottom anemone's position. b.y equals top gap plus game settings dot obstacle gap underscore top gap equals t dot get bounds bracket GUI module settings dot stage ref dot bottom, and bottom gap equals b dot get bounds brackets GUI module settings dot stage ref dot y. Thanks for watching.